Yes,
Okay.
we did it at first anyways,
Okay.
because I haven't assigned it yet. We had to skip it at first because we hadn't done triangular distributed loads yet, but we'll do it. Okay, so first, here's the news coming up. So Monday is a quiz. It's just quiz 2, I think. We're going to have to start having a lot more quizzes. But Monday. Oh, that's good. That's good news.
Because I missed one in that Don one.
Okay.
We only have quiz 1, but don't hit the test.
I don't think I missed a test. So maybe I missed the one quiz. I don't know.
Okay, it's a quiz. We can all agree on that, right? It is a quiz. So Monday, Halloween. It's the Halloween quiz. It's the witching quiz. Remember, those are cumulative. The way to get ready for it is to skim back through your notes, categorize stuff in your head, make mental notes of the big points. Statics is actually sort of a hard class to make quizzes for because there's not a lot of information. It's more just like getting used to approaches and stuff. But anyways, so quiz on Monday, and then exam. This one I know is exam 2, is Friday of next week. And that I think is the 4th. And these are also cumulative. It's not going to have any internal loads. It's just up through structures. Statics is such everything builds on the last thing so much in statics that you can pretty much just always do whatever the current topic you're doing is, and it'll cover all the old stuff. But remember, there can be particle statics. I guess that's the one thing that we don't talk about too much right now, but it's easier than rigid body statics. But so that's next Friday. And then after Friday or on Friday of next week, I'll give you the next weekly assignment, and I'll get your last weekly assignments graded, the ones you've turned in. Any questions about that? Okay. We have like a month, and like the semester is going fast. 5 weeks, it's crazy. All right. Any homework questions you'd like me to go over? We're in the middle of an example problem. Okay, so let's go back to the example from Wednesday. So the problem was this. You have a beam, the roller at the middle, and a pin joint at the right end. You're pulling on it over here with a 500 Newton force, and there's a triangular distributed load. That ramps up to a value of 2,000 newtons per meter on the right. And it has a total length of 3 meters, so each of these distances is 1.5 meters. There are 2 cuts. We did the first cut already. So cut 1 was for x values between 0 and 1.5. And we got that t is equal to 500 V is negative 333.33 x squared, and M is equal to negative 111.11 x cubed. And we did the derivative checks on this. dm dx is equal to V, so that's good. Negative dv dx is equal to Q. Remember that we figured out that our Q function, since it's a line, we just need the equation for that line, and it's equal to 6, 6, 6, 6's forever, x. And so negative dv dx is equal to Q, so that's all looking good. So now we're going on to cut 2. This is for x values between 1.5 and 3. Okay, so what does this look like as a free body diagram? So now, no matter what x is in this range, we've gone past the right end has gone past the roller. So now we have this 2,000 Newton force from the roller. We still have the 500 Newton force on the left end. We have this distributed load. And we have the internal loads, T, V, and M. This distance is x. The left end is x equals 0, the right end is x, and so we can use the Q function to tell us what the value is here. That's just 6, 6, 6, 6 is forever, x. But we can't do Newton's laws from this. Now that we've chosen the body to isolate, now we can finally represent that distributed load as a point force. So let's see, I'll go over here. This looks exactly like it did on the first example, on the first cut. But we have a length of x, a height of 6, 6, 6, 6 is forever, x. The centroid is 2x over 3 from the left. The area is x times the height divided by 2, so 3, 3, 3, 3's forever, x squared. So now I'm going to draw a new free body diagram. We have the 500 Newton force on the left. We have the upward force of 2,000. We have the downward force that represents the distributed load, 333.33 x squared. And then we have the internal loads. Okay, and so the distances that matter, the distance to where the distributed load is, where that point force is, that's 2x over 3. the distance from the left to where that point force is 1.5. And the distance from the left to the right endpoint is x. One thing, by the way, that might confuse you at some point or other is, you have to, on something like this, like you have to choose, like this, the distance from the left to this 2,000 Newton force is 1.5 no matter what. The distance from the left to that point force for the distributed load changes depending on what x is. So for some values of x in this range, this is going to be to the left of that. For some values, it's going to be to the right of that. And you're going to be like, oh, which one do I draw, And does that mean I have to do separate cuts? It turns out it doesn't matter. Just choose one and draw it. Are you with me what I'm talking about there? The math will work out all that stuff on its own. So just choose one and draw it. Okay, so now Newton's second law. So negative 500, 0, plus, okay, now I'm going to keep emphasizing this because it keeps being, it like never stops being confusing to people almost. But the way to think about it, so what's the sign of this vector? Think of it as a unit vector times a scalar, okay? The unit vector is 0, negative 1. You're multiplying it times 333x squared. And so that's 0, negative 333x squared. Then 0, positive 2,000. Plus m minus vx. Wait, what am I doing? I went crazy all of a sudden. This is Newton's second law. So 2t minus v is equal to 0. Okay, so t is equal to 500 over this whole range. V is equal to negative 333, 3's forever, x squared plus 2,000. And now the moment equation. Our about point is at the left, always. Okay, so the 333x squared has a moment arm of 2x over 3. Is that a clockwise or counterclockwise rotation? Clockwise, so it's negative. Then a moment arm of 1.5 and a force of 2,000. Is that one clockwise or counterclockwise? Counter, so it's positive. Then plus m minus vx is equal to 0. So m is equal to v times x plus 222.22x squared minus 3,000. Yes, that was a test. Okay, that's x cubed. And so m, so now the Vx you take that function for v that we just found above, multiply it by x. So we have negative 3, 3, 3, 3's forever. X squared times x is x cubed. Plus 2000x. Plus 2, 2, 2, 2's forever, x cubed, minus 3000. And now add up the cubes, and you get m is equal to negative 111.1's forever, x cubed, plus 2000x, minus 3000. Let's check the derivative relationships. Because now we're done with all the internal loads. The derivative relationships worked out for the first cut. For the second cut, so dm dx is negative 333 x squared plus 2000. That's v, so that's good. And then negative dv dx is negative 666x. That's q, so that's good. And there are times where you'll do your calculation, those derivative relationships won't hold, and it'll help you find your mistake, or you'll be like, screw it, I'm not doing that again. But at least you know that you're turning in something wrong and that I'm disappointed in you. Okay, so so if you have those rectangular distributed loads, so if you don't have a distributed load, first of all, your shear forces are constant, piecewise constant, and your bending moments are piecewise linear. If you have a rectangular distributed load, like a constant distributed load, your shear forces are piecewise linear, and your bending moment is quadratic, piecewise. And if you have a triangular distributed load, your shear force is piecewise quadratic, and your bending moment is piecewise, whatever that's called, cubic, I guess. And then, depending on what that function is, I mean, your q could be to the power of 8 or whatever, and then you keep getting more and more complicated looking functions. But for the and by the way, so if that happened, like I'm just using simple area calculations and stuff, but you can calculate the centroids and areas of complicated functions, distributed load functions, by just using integral definitions of stuff. I'm not going to make you do that, but that's how you would do it if you had to. The example I did before, it wasn't too hard to come up with, to just like by hand come up with those diagrams. But this is sort of a mess, so I did it in Excel. So here's what the tension is easy, right? The tension just goes 500 the whole way. Is it in tension or compression? Tension. Positive is tension, negative is compression. And then the other ones that are harder to visualize, I might have put it there. So the shear force is piecewise quadratic. The bending moment is piecewise cubic. Well, this tells sort of an interesting, you're starting to get some information about where you're concerned about this beam breaking. There's something weird going on at 2.5, a little before 2.5, and there's definitely something you're concerned about as you get near to 1.5 meters, the middle of the beam, and that's all stuff that you wouldn't have known without doing this analysis. To get more details, you'd have to calculate the stresses and strains, though, which is what the next step that we'll take in deform on a problem like this. Any questions about that? Okay, so now I want to give you so these are like the checks on your answers. These are 5 relationships that must be true for internal loads. The first 2 are the derivative relationships. I've been talking about those, but I don't think I've written them down yet. So dm dx is equal to v. The second one, negative dv dx is equal to q. The negative is just because we happen to call q, like we call q positive when it's a downward distributed load. There's all sorts of weird sign conventions here. The third one is, so 3, 4, and 5 are very similar to each other. At the endpoints, t is equal to 0 if and only if there's no horizontal point force at that endpoint. We'll go back and check all these after I get them all written down. So that's the one on the internal tension at the 2 endpoints. 4. Okay, so if there's something like this for T, what would you guess the last 2 are going to be? V and M, that's right, yep. So same exact thing, the wording is all the same at the endpoints. V is equal to 0 if and only if there's no, what do you think is going to be required here? Exactly. There's no vertical component or vertical point force at that endpoint. And then 5 is the bending moment one. So at the endpoints, M is equal to 0 if and only if, what do you think the requirement is for the bending moment? Point couples, yep. At that endpoint. There's two ways couples can come up in these problems. The first is that there's some kind of applied couple that's written on the problem, you know. And then the second one is that it's a fixed joint. In 2D like this, a fixed joint is the only joint that applies a couple. Okay. All right, so we already checked the derivative relationships. Let's check at the endpoints. So t equals 0 at the endpoints if and only if there's no horizontal point force. Okay, so are there horizontal point forces at either of the endpoints? Yeah, there's actually, they have them at both of them, right? There's the applied 500 at the left, and there's the one from the pin at the right. So that should be non-zero at both ends. You could figure out the signs if you wanted to. Oh, right, I don't have a diagram of t, but our function said it's 500 the whole way, so that one is fine. Okay, what about v equals 0? So let's look at the endpoints and see if there are any vertical point forces. There's no vertical point force on the left. There is a vertical point force on the right. So we expect shear force to be 0 at the left, non-zero at the right. And we have that. Okay. That value at the right is equal to the point force at the right. Well, with sign, you know, you have to think about the signs a little bit. And then the last one, there are no point couples anywhere. So we expect the bending moment to be 0 at both ends, and we have that. Okay. There are other problems that can come up that doesn't prove that you did this right, but it can find a lot of the mistakes that you would make. And notice that, so I mentioned the thing about, like, you know, definitely the most work in these problems comes in the moment equation, you know. Like the other two are just like immediate kind of, but we had to go through all these steps in the moment equation. So I mentioned that, like, you might think like, oh, I'm just going to integrate v with respect to x to come up with m. And you can do that. And there are easy, you know, pretty simple rules you can follow to come up with the boundary conditions. But just notice that, like, so it would have worked to integrate v, knowing that there were no point couples at the end point, so we had to start at the left end at 0. And then here, this wasn't one of our checks, but since there's no point couple at that point, there's not going to be any jump in the m value there. And so that would be your boundary condition, that you have to match up the m values at x equals 1.5. Okay. And, okay, also, you'd need 2 boundary conditions for this one. Is that right? Anyways, I would have to think about that a little bit, but anyways, you would also know that since there's no point couple here, you know, that has to be equal to 0. And you can match that up with your, but it's sort of a pain. It's not really any easier to do than just going through that. Either way you did it, you would, I mean, I think it's good to have in the back of your mind that that's a thing, you know, but either way, I think you'd want to do it the other way and check your answer because there's a lot of mistakes you can make, you know. Any questions about that? Okay. I'm not going to get into this next thing, but let me just tell you what we're going to do next. And we're going to do this because we are doing vector and matrix calculations, and it allows us to do this. So the next thing is, say that you had a structure. That's not pretty straight. That's better. Okay. Pin joint there. Each one of these has a mass of 50 kilograms. Let's say this is an equilateral triangle. So, well, let me just say these angles are the same, and the length is 1 meter. And let's say that there's a force here of 500 newtons and a force here of 1,000 newtons. What are the internal loads in each member? Okay. Well, we know that's not a particularly complicated structure to solve. You've done problems like that. But once you've solved the structure and calculated the external loads on each of those things, you have your external loads calculated in a coordinate system oriented like this, you know, and you have, compared to that coordinate system, you have the beam at a funny angle, you know. So we haven't done any internal loads like that before. How do you re-express all of your loads in a coordinate system that's oriented with the x-axis along the beams? You know what I mean? And then for this one, depending on which side you're thinking of, let's say you want to use a coordinate system like this, you know? And so if I number these, let's call this member 1 and this member 2. For member 1, we need to re-express all of our vectors in a coordinate system that's rotated like this. That's a positive 60-degree rotation. Because what we have then is we have that. And now we're not used to doing internal loads like that. How do we get from this to a thing where the thing is lying flat and the coordinate system is flat like we're used to? You turn your head a little, because that's what that means. you know, we don't care about just rotate the paper or whatever. This is the same thing as this. Number 2, we want to go from this coordinate system to this one. That's a negative 60-degree rotation. And then, so then we'll have our coordinate system like this, which is equal to this. Okay. So I'll start getting into using rotation matrices to re-express our external loads that way next time. Any questions about that? Okay, that's all. Have a good weekend.
Did you actually get stuff on number 10 and structures that you said? I remember there not being any like answers for it. But
For structures, oh, did it say something about internal loads?
yeah.
Oh, then that's just a mistake. Sorry, little by little. Oh, you did. Oh, that's great. Well, you can do it by like eyeballing. I mean,
Yeah.
it's a little bit of a pain, but you can just re-express each component using cosine and sine.
Yeah.
But you're gonna like using rotation matrices a lot better.
Okay, sounds good.
Okay, sorry, I did not mean to sign it that way. What that means is that it used to be in a different set of problems, and then I was like, I'm gonna move it to this set, and I forgot to adjust the questions it asked.